And Lauren, I know you're out there, so I'm not that good at looking at the chat. So if any questions come up, just holler at me. Okay, so let's kind of pick up where we left off. We were looking at sort of our practical way of finding Galois groups for polynomials. And I've got a kind of a cautionary story that comes along with this. So let's look at this example here. Where F one x4 two x4 plus and x minus 2. So was anybody able to figure this all out? Okay, so let's get this part of it. Okay, so let's find the result of cubic, and I'll sort of remind you of the formula that we've got here. This would be f of x, which is x4 plus ax cubed plus bx squared plus cx plus b. And resolve cubic. The result of cubic is x cubed minus bx squared plus ac minus 4dx. Term here minus a squared d plus 4d. Okay, good. So let's find the result of cubic here. So in number one, what we have is A is 0, B is 4, C is 0, D is 2. All right, so resolve the cubic here. Minus 4 x squared. And we'll see AC minus 4D. Well, that's going to be minus 8x. And finally, get this big mess here. A is 0, D is C is 0. So these two are gone. And I just get 4BD, which is 32. So there's your result of cubic, which looks pretty bad, right? But it's actually not so bad. Go right here. So, what is the degree of the splitting field of this over the base field K? So if you take this What's that is that thing that we call K alpha beta gamma. What's the grid splitting field right? Well, that's a red herring, right? Because 4 is already given, right? So we sort of forget about this 4 there. And then we have 2 other roots, basically. I mean, the splitting fields. Anybody identify the splitting field? Square root of 8, which is the same thing, square root of 8, right? Field wise, that is. So M is 2. Now, the question is, so this is our case. So M is 2. So he is isomorphic to cyclic or E4. One of these 2, right? And the distinction is made, and it's D4 if and only if
what is G?
the Galois group.
Over all of them or over just this one?
No, we're doing number 1. It's just number 1. We'll come back to these other ones. This is D4 if and only if F is irreducible over which in this case is Q radical 2. Well, let's look at this polynomial here. Does anybody see how we get back to this? Let's look at the polynomial. What we have to do is kind of test to see if this is this or is this not irreducible over this intermediate field. Well, let me write this as now the roots of this are 16 minus 8 is 8 over 2. So this is minus 2 plus or minus bracket 2. So my polynomial here becomes which equals so this reduces. Because there we go. I don't care if it reduces further or not. Okay. So this reduces over this field. So Galois group, this one is isomorphic cyclic 4. Any questions? All right, let's do two. In this case, my polynomial is, got this one done, x4 minus 10x squared plus X is 4 minus x squared plus 4. So here I get the result of the cubic. X cubed plus 10x squared. I guess that's going to be the minus 16x. And that last bit is going to be minus 160. That's what it looks like to me. And this is the same kind of trick here. This is x squared times x plus 10 minus 16 . Now, what's the splitting field of that over Q? We're already there. Okay. So in this case, we have M1, and so G, in this case, it's isomorphic. C2. For the last, well, any questions? For the last one, for number 3, let's get to resolve the cubic again. I'm really digging on the last one because D is -2 and everything else is 0. Right, so my resolving cubic here is x cubed. There's no quadratic term. D is what, -2, so this is plus 8x. And D is the only non-negative and it's paired up with 0, so there you go. There's your resultant cubic right there. You can't beat that with a stick, right? So this is what's the splitting field now? Over Q, say, right. So really all you need is the square root of -8, which is equal to the square root of -2. Right. So again, we have m equals 2. So this boils down to if and only if it's the 4 minus 2 is irreducible over and actually this one's fairly easy to figure out. So the roots of this polynomial are 2 to the 1/4 minus 2 to the 1/4. I to the 1/4 minus I. right? So the factors are notice that none of the linear factors are in here, right? So everybody agree with that? None of the linear factors are in here. So if this were to factor, it would have to factor into two quadratics. Agree? Now, think about it this way. How do you make quadratics? Well, if you pair these together, then your problem is 2 to the 1/2 is not in here. Right? So you can't pair the reals. So you've got to pair this with one of these two, right? And in either case, you get a cross term that's not in here, right? So I get you. And this is probably not too much of a surprise because this, in a certain sense, spiritually is kind of similar to, some of these other ones that we have like this. So I'll expect not to be able to get one. Okay, let me give you a theorem and then kind of a funny cautionary story. This one is kind of a mindful algorithm thing to tell. So this is kind of a good check. This is actually mostly useful. If you do this with my hand, it's mostly useful to find out if the Galois group is a symmetric or an alternating group. Suppose f of x is a monic polynomial. By the way, you can generalize this to other rings of the Z, but I'm just going to stick with this now. Degree. And actually, you don't really need monic, and I'll explain the importance in a moment. Let P be a positive prime Z. You also assume that the reduction of f of x mod p has distinct roots. So in particular, I want f of x. I want f of x to be a separable polynomial, and even if it is a separable polynomial, I want it to be separable mod p. So if I reduce mod p, the polynomial could have distinct roots. But let me give you kind of a for instance, right? What if 2 of the roots are 4 and 7, right? In mod 3, those 2 roots are the same, right? Because 4 and 7 are equivalent to mod 3. Then I wouldn't use 3 to perform this test, right? So you've got to dodge all the ones where it's not separable mod p. Then f of x factors. Well, let's see. If f of x factors is g k. Over z mod p. With, and it says they're each g I x in the principal. Over z mod p z.
That factorization is in the same page.
Yeah, of ZPX, right, yeah. That's factorization of polynomials with coefficients. Deal. Degree of HGI x equals MI. So the degrees of the polynomials by ZI. Then there exists an element of the Galois left of x over Q of C1, C2, where CI, C1, C2, K are disjoint sets. Length. So what this theorem tells you is, suppose you have a polynomial here, coefficients C, and you want to know some stuff about its Galois group. Reduce this mod p, and if you get a separable polynomial, then factor it. Right? If the degree of each thing in the irreducible factors is mi, then there must be an element of the Galois group that is a product of exactly k disjoint cycles of, and each length is the length of the degree. Right? So this is actually kind of a good thing. And let me give you an application. And you're going to think that I've completely lost my mind, because for you to appreciate my little story, I've got to do it for you, I guess. So how many of you have taught your own class yet? Made up a quiz or anything? So this is a cautionary tale for you. Example. So here's a calculation. Well, find value of such that the area under parabola well, This is a fun little calculus problem. So find what it takes, right? Because I mean, you can vary the slope. Isn't it clear that at some point this will cut the area exactly? Right. What is value? So let's do the problem, shall we? Total area. Under the problem brackets. Is that agree? So this is A and so I get like 160. Okie dokie so far. So by the way, just for fun, what I need is either the top piece or bottom piece to be 112A. Which one do you think is easier to do? This is certainly an opinion question, right? But my opinion is I want to find this to be 112A, right? Above the line. Anybody want to guess why I think that? For sure, if you do it under the line, then you're going to have two intervals to do, right? Because for a while the roof is the line, and then it's the parabola, right? So I'd rather do this. In any case, no matter how you cut this pie, you're going to have to figure out the intersection point, right? And so all I really care about is the x value, and the x value turns out to be set this equal to this, and you get something like 1 minus m over there. Right, because when you take that value, you get m minus the square root of a. Anyway, so maybe I should check myself. So the intersection point is not 0, and so I get the intersection point is not 0, and so I get x equals yeah, that's fine. Or if you like, everybody okay? Okay, so now here's the heavy lift again. We want this area 112A. So this is the interval from, and I'm going to call this alpha, just so I can write this at the last moment. This is the interval from 0 to alpha of top, which is the parabola, minus the bottom, which is in x. So this is ax squared over 2 minus ax cubed over 3 minus m x squared over 2 evaluated from 0 to alpha. And lucky for me, when I put in 0, it's 0. So if the equation 112A is equal to let's see, I guess a minus m alpha squared over 2, and then minus a alpha cubed. So 112 A is A minus M. And this is going to be, I'm going to use this representation. A minus M. Half of this, because half there, minus 1/3. A times A minus M cubed over A. So this looks like a disaster, but this is going to be 1/2 A minus M cubed over A squared minus 1/3 because the A is canceled. Convenient, right? So this is going to be 1/2. Let's see, this is the same quantity here, so this is going to be 1/6. Squared. And so I get, let me get rid of this 12, I'm really sick of it. I get A cubed equals 2 A minus M cubed. Now take the cube root of both sides. And so what do I get? Well, I've got to solve for M here. So 1 over the cube root of 2 times A is A minus M. And so I get M equals A times 1 minus 1. So that's exactly the slope of the line that you need to cut that out. Remember saying it, right? I put this on the calculus test, right? The calculus, setting it up requires a little bit of thought, right? And of course, doing it this way, I think is easier. What do you got to do in this problem? You got to find the intersection points. That's algebra. Actually, the calculus is very easy, right? The calculus is just integrating, a couple of quadratic polygons, right? And so I'm like, okay, I get it. Most of my students are not going to get all the way to the end here. So, getting all the way to end game is like, if you get somewhere in here, you got 9 out of 10, right? Kind of thing. Right? Okay with that? Well, so here's the cautionary part of the tale. I gave this exam, people took it, good for them. But of course, when you teach a large lecture class, the mortality rate for grandparents goes through the roof. And that's what I had this particular semester. And I had various people taking makeup tests, so I gave makeup tests. And I had this one galactic doofus who ghosted me like 2 times on the makeup test, right? So I had to make up another makeup test. And I never finished this one's makeup test because he, like I said, he ghosted me a couple times. And finally shows up unannounced in my office one day when I was working, was, "Can I take the makeup test now?" I was like, "Yeah, come sit down." So anyway, I get the test out, the latest version, and I still had to replace this problem for his test. Now, this was kind of the centerpiece problem on the previous one. So I'm like, well, I can't give him anything easier. And, I used up a whole bunch of problems on other people and I was doing other things. So I was like, oh, how can I change this so it's not easier and it's the same kind of thing? I said, oh, I know what. Brilliant idea. Here's what I'll do. I'll give him the same problem, only this is the volume about x-axis. So in other words, now you take this region and you spin it around the x-axis, now adjust the slope so that it cuts the volume into 2 equal pieces, right? Same thing, right? Well, I challenge you to work this problem out. So I gave him the problem and the other problems, set him down to take his test. And out of curiosity, I went back and did the problem myself. And, you know, the algebra here is bad enough. It gets worse. Believe me. And I had to do all kinds of, I mean, I was using Gandalf's staff and everything else on this thing. And I finally reduced it to the polynomial unity. For m over a. So if you can find the ratio in the a, then you're good to go. So the polynomial that you need, and actually the first iteration I came at with a 10th degree polynomial, but I was able to reduce it by doing something. You basically need to extract roots from this polynomial right here. And of course, I saw that 5 there. Oh. Let us apply the previous theorem and see what the Galois group is, shall we? What is the Galois group of this polynomial? Now, I won't make you prove this here, but this actually is in fact an irreducible polynomial of the rations. It's not monic, which may scare you a little bit, but that's okay, because even though I said monic with the previous theorem, this polynomial sort of is monic, except for the prime 2. 2 is the only prime that divides the leading coefficient. So mod 3, mod 5, it's all good. So really all I need is for this to be separable when I do it, right? Now, let me ask you this. Right out of the gate, given that this is irreducible, what are the choices for my Galois group? Has to be a transitive subgroup of S5, correct? C5 has to be one of these. Has to be symmetric group, alternating group, has to be Frobenius group 420, has to be dihedral on the 5 gon or cyclic 4-5. It's got to be one of these. So I won't make it go through all this stuff, right? If you try to reduce this mod 2, and again, it's not mod 2, you know, you get the polynomial 1, which isn't really helping anything out. But it turns out that if you reduce this, mod 11, this is what I got, and I will verify this works. I get the following polynomial. X squared plus 9x plus 6. And what else does I have? X cubed plus 9x squared plus x plus 3. That's what I got. Let me check this out. Let's make sure, because this is computation here. This is 8 times this is going to be x5, and that's going to be 9 and 9 is 18, x4 plus let's see, let me go cubic term now. Oh yeah, here we go, cubic term. I get 1 and 81 is 82 and 6 is 88. And it's cubic. I need 40 or square term out. I get 3 and 9 is 12, 54 is 66. I need a linear term, which I get 27, and 6 is 33. And finally, I get 18. Now, plainly, I get 8x to the 5th here, no problem. That's 144, right? But mod 18, or yeah, that's 144. So mod 11, that is, that's going to be 1 mod 11, which is minus 10. And these three are divisible by 11, so they're gone. And finally, I get 144 again, which is plus 1. So this works. Everybody agree with that? The last thing that I probably have to do, so I don't need this anymore, is I need to check, are these irreducible? But it's easy. Can somebody explain why it's easy to check, say over the field of 11 elements? Why is it easy to check whether or not these are irreducible?
They're reducible, they have at least one linear factor, so you have 11 choices.
That's exactly right. That's exactly right. If this reduces, it plainly has to reduce into 2 linear factors. And no matter how you cut the cake on this one, you've got to have at least 1 linear factor. So the reason it's easy to check this is all you got to do is go through the mod 11, 0, 1, 2, all the way up to 10, plug these in and see that there aren't any roots. And I'm not going to put you through that, but trust me, these things do not have any roots mod 11, so they're irreducible. Our theorem says that, and of course, these polynomials are all separate. We're going to see later the finite fields are always separable. So since these are irreducible polynomials, they have to have the same root. They're separable. And so the Galois group of F has an element. Form A, B, C, D, E. It has to have a product of a 3 cycle and a 2 cycle that are disjoint. Can anybody tell me if you multiply a 3 cycle and a 2 cycle and S5 together, what's the order of this element? It is 6 because these are disjointed. It's the least common multiple of the orders of the elements in it. So the Galois group contains an element of order 6. So off the table now are these 3. Right? Because the order of this is 5, 10, and 20 respectively. It's not going to be plus 6. So now we are making the choice between S5 and A5, which is correct. How do you know it's S5?
Your A5 elements. That would be
What's the definition of A5? What does A5 consist of? It's all the elements of S5 that are
signature.
okay, right. S5 is all the even elements, right? This element is odd because that's an odd cycle. So this is an even permutation. One more even permutation. This is odd. So not A5 even. So it has to be S5. Which made me chuckle because that means that, and we're going to see this soon. How many of you are, everybody knows the quadratic formula. How many of you have seen the cubic formula at some point in travels? Yeah, it's awful, right? Nobody's going to teach that in high school, right? Because it's, I mean, it's really kind of a beautiful thing, but it seems like rote memorization. How many of you have seen the quartic formula? you can find that in some books and so forth. That one is unbelievable, right? Because what you have to do is you first have to evaluate a cubic, and then it's just awful. It's awful. I mean, it's basically kind of the steps that we went through in determining the Galois group. You have to find roots and resolve the cubic and then do something else, and it's death on a hot plate. How many of you seen a fifth degree formula? There ain't one, right? And I mean, it can't be done. There is no formula for general quintic. If your Galois group is one of these three, it's a solvable group, and you can find the roots in terms of radicals, right? And we'll talk just a little bit about that later. But these two are not solvable groups, and so there is no formula in terms just purely of radicals and being able to find that. So my poor little student, this is like a cautionary tale about showing up for makeup tests, I guess. Okay, next time, which will be Monday, and don't forget that'll be remote. I'm going to give you a neat little result that shows how to figure out any Galois group, and it always works, and you should never use it. But at least you can take comfort from the fact that it's out there. You'll see very quickly why you don't want to use it, but it always works. Okay, any questions? All right, seriously, put some thought into coming to math up today. It looks like it's going to be a really cool one. And other than that, y'all have a good weekend, and we'll see you on TV on Monday.